So, today we are going to start the topic of discretization. Okay. So, in this topic we are going to cover, after a brief introduction, the discretization of various kinematic quantities. Okay. This is very essential for getting the final finite element form. Okay. Then we will get the discretized version of the continuum equilibrium equations in finite element form. And finally, we will discretize the linearized equilibrium equations that we derived in the previous lectures. Okay. So, each of these topics is very involved, and I suggest you work it out on using pen and paper. Okay. So, in the previous lectures we have established the equilibrium equations, and also we had obtained their corresponding linearizations, both in the material or the Lagrangian configuration and the spatial or the Eulerian configuration. Okay. And as stated earlier in the previous lectures, either of the material or the spatial descriptions can be used to derive the finite element discretized equilibrium equations and the corresponding tangent matrices. Okay. However, it was also mentioned that it is much simpler to establish the discretized quantities in the spatial configuration. Okay. Also, we like to point out at this point of time that the derivation of the components of the tangent matrix, okay, is very involved process. Okay. And this will take a lot of time to understand and get used to. Okay. So, the components of the tangent matrix get their contribution from the constitutive relations, from the initial stresses, and also from the external forces. Okay. External forces, because if you have pressure dependent loading or follower loads, in that case you will have a contribution to the tangent matrix which comes from these external forces. But we have mentioned in our previous lectures that we will not going to consider these kind of forces in this course. Okay. So, in this course we are not going to discuss those kind of forces. So, we will not have contribution to the tangent matrix because of external forces. We will only discuss the contribution of the tangent matrix because of the constitutive relations and the initial stresses. Okay. And once we have derived the tangent matrix, we can set up the Newton-Raphson solution technique to get the desired solution. Okay. Now, let us come to discretization of kinematic quantities. Before we can start linearizing our equilibrium equation and also discretizing their linearized expressions, we first have to discretize the various kinematic quantities. Okay. Now, in the present course we use what is called isoparametric finite elements, which means that the shape functions used to describe the geometry and also the shape function used to describe the primary variable, in our case which is displacement, are one and the same. So, we use the same shape function to characterize the geometry as well as the primary variable. Okay. So, let us consider a typical finite element at finite element E at time 0, okay, and let the volume of this element be dV 0. Okay. Not to confuse with the volume of the body. If you are confused, just put a subscript E. Okay. Then after deformation, let us say this element deforms and gets this final shape. Okay. And this volume is dV, you can put dVE if you wish, I will not use that. And let us say d capital A is the area on which the external forces act. Okay. So, it might be pressure loading, it might be any kind of other kind of surface loads, but this is the area on which the surface forces act, and this area deforms and you get d small a. Okay. Remember, this is one finite element of the entire finite element mesh of the body. Okay. And xi 1, xi 2, xi 3 are the natural coordinates. Now, let us consider two nodes P and Q. Okay. And if you are very consistent, we can put capital P and capital Q. Okay. And after deformation, these nodes go to this location P and Q. Okay. Let del V P, okay, subscript P means it is a virtual velocity of node P. Okay. So, P and Q are the nodes of these elements, and del V P is the virtual velocity associated with node P, and let U subscript Q be the displacement corresponding to node Q. Okay. In 3-dimensional, usually these are 3 cross 1 arrays. Okay. They have 3 components. In finite element, they will have you will write them as a vector of 3 cross 1. Okay. So, with this setup at hand, the first thing we want to do is we want to discretize our various kinematic quantities that we discussed in the course till now. Okay. So, first we take the initial geometry, okay, that is the geometry of the body at time t equal to 0. So, the initial geometry in terms of the particle defining the initial position of the elemental nodes of an element E is given by x equal to n1 x1 plus n2 x2 all the way up to nn xn, and in terms of summation sign I can write this as p equal to 1 to n np xp, okay, where n1, n2, n3 all the way up to nn are the shape functions. So, what it means is inside the element E, okay, the material position of any point can be interpolated in terms of capital X1, capital X2 all the way up to capital Xn, where capital X1, X2 are the nodal material coordinates. Okay. So, this small n denotes the number of nodes the element has. Okay. So, n denotes the total number of nodes belonging to the element E. Okay. So, in case if you have a brick element, okay, which is like a cube, so your n will be equal to 8. In 2D, if you have a triangular element, n will be equal to 3. In 2D, if you have a square element or a quadrilateral element, your n will be equal to 4. Okay. If you have a 3D and a tetrahedron, in that case, you have n equal to 4. Okay. Like this, n can vary. Okay. So, the material point inside an element, okay. So, this is the element, okay. So, this is a finite element E, and any material point inside this, its position can be interpolated in terms of the nodal positions x1, x2, x3 all the way up to xn, okay, where n1, n2, n3 are the shape functions associated with node 1, node 2, node 3, okay. And these shape functions are, okay, for the pth node of the element E, and they are written in terms of the natural coordinates psi1, psi2, psi3. Okay. So, for better description, I can write equation 1 as, okay, so this is x. So, this is the material location inside the element, and that can be written in terms of n1 times the material location of node 1 plus n2 times material location of node 2 all the way up to nn into material location of node n. Okay. So, here x11 means the x1 coordinate of node 1, x21 means x2 coordinate of node 1, x31 means x3 coordinate of node 1. Okay. So, equation 1 explicitly can be written like this. So, this is the only time I am writing like this. In coming slide, I will not write. Okay. So, you can understand what actually equation 1 means. Okay. Wherever we have a equation which is analogous to equation 1, you can understand that this is what we mean. Okay. So, in traditional finite element, equation 1 can also be written in terms of matrix vector multiplication given as x equal to matrix n multiplied by a vector x c, okay, where x remains as it is, it is the material location of a point inside the element, okay, and x e is nothing but the vector, okay, formed by the material location of all the n nodes. So, this is x 1 is node 1, okay, and these are three entries. So, x 2 is for node 2 and also these are 3 entries like this. You have node n and these are 3 entries. So, all in all this is 3n cross 1. Okay. So, the matrix n can be written, okay, in this particular form. Okay. You can do for yourself, you can substitute it here and you can substitute this here and you will see that you can get equation 1 back. Okay. So, n is called the shape function matrix, okay, because it is composed of entirely of the shape function, and you can also notice that there are a lot of zeros here. Okay. There are a lot of zeros present. Okay. So, in fact, out of 9 entries, 6 entries are 0. So, there are 2/3 0, okay, out of total entries 2/3 are 0. So, if you use equation 2, you will in computational setting, you will be having a lot of 0 multiplications, and you understand that multiplying any quantity by 0 gives you 0. So, equation 2 basically leads to a much more computationally expensive process, though it does not change the result. Okay. Now, the current geometry, okay, in terms of the current particle position of an element E can be discretized as given by this equation. Okay. So, small x is the current spatial location of material particle x. So, x is psi of x comma t. Okay. So, this is your t here, okay. And then the current spatial location can be interpolated in terms of the current spatial location of the nodes of element E. Okay. So, it is x equal to n 1 x 1 plus n 2 x 2 all the way up to n n x n, or in short n p x p which is a function of time t. Okay. Okay. So, as usual I can write this in matrix vector notation as x equal to n x c, okay, where the form for various arrays is given here. Okay. Again, n has the same form, is the shape function matrix which was described in the previous lectures, okay, or the previous slide. Okay. Now, we can differentiate equation 3 with respect to time and we will get what is called the velocity. Okay. So, velocity is del x by del t, and we can get the expression for a velocity at a point inside the element in terms of the velocity of the nodes. Okay. V 1, V 2 all the way up to V n are the velocity of node 1, node 2 all the way up to node n. Okay. And in short it is n p V p. Okay. And this is the usual matrix vector notation expression, and these are various. Okay. So, this is the component of the velocity of the point, and these are the component of the velocity of node p, and V e is nothing but the velocity vector, okay, composed of velocity of all the n nodes. So, as usual this is 3n cross 1 array. Okay. Now, the virtual velocity can be obtained by taking the virtual of equation number 5. Okay. So, virtual variation you take, you will get the virtual velocity of a point in terms of the virtual velocity of the nodes, okay, and this is nothing but n p del V p. Okay. And as usually the matrix vector notation helps us to write equation 7 more concisely as given in equation number 8. Okay. And these are the virtual velocities of a material of a spatial point inside the element. This is the virtual velocity of node p, and del V e is the virtual velocity composed of all the nodes of the element E. Okay. Next, the displacement at a spatial point can be obtained as u equal to n1 u1 plus n2 u2 all the way up to nn un, or in short summation over the nodes np up. Okay. In matrix vector notation, the displacement at a point can be written in terms of the shape function matrix and the elemental displacement vector. Okay. So, this is the element displacement vector, u is the displacement of a spatial point inside the element and up is the displacement of the node p. Okay. So, each node will have 3 displacements in 3 directions. Okay. Next, we come to the spatial gradient of the displacement at a spatial point x. Okay. So, the spatial gradient, okay, of a displacement at a point inside the element can be obtained as del u by del x, and we know that u is summation over all the nodes np up, and therefore, the gradient will be del by del x of this summation over all the nodes. Okay. So, if I bring that inside, I can write this as up tensor product del np by del x. Okay. And then I can use the nabla symbol and I can write in short this as up tensor product del np. Okay. And we will see how to compute the gradient, spatial gradient of the shape function. Remember, np are given in terms of psi 1, psi 2, psi 3 natural coordinates. Okay. So, carry out the spatial gradient of these shape functions with respect to natural coordinates, okay, with respect which are a function of natural coordinates, we have to do a special procedure which will come later. Okay. So, that is equation 11, which gives you the spatial gradient of the displacement at a spatial point. Okay. Now, the spatial gradient of the velocity vector at a spatial position x, which is nothing but the velocity gradient tensor L, is given by L equal to del v by del x. Now, I can substitute v as the interpolation, okay, of the velocity vectors of the nodes, okay, which is shown here. Okay. So, then the velocity gradient will be del by del x of this quantity in the bracket. So, again if I open up the bracket, I will get V p tensor product del np by del x, or in short I can write V p tensor product gradient of np. Okay. So, that is my velocity gradient tensor. Okay. Next comes the deformation gradient tensor. So, how can I write the discretized version of the deformation gradient tensor? So, the deformation gradient tensor over an element E can be obtained by taking the differentiation of the spatial position, okay, that is equation 3 with respect to the initial or the material coordinate. Okay. So, that is what we know, f is nothing but del x by del capital X, the differentiation of the the spatial position with respect to material position. Okay. So, x is nothing but np xp, okay, and then I take the material derivative of the summation over all the nodes np xp. Okay. So, if I open up the bracket, it becomes xp tensor product del np by del x. Okay. Now, in short I can write this as del 0 np. Okay. Remember, del by del x can be written as delta and del by del capital X can be written as del 0. Okay. So, the deformation, the discretized version of the deformation gradient tensor is given by equation number 13. Okay. So, in initial notation, the equation 13 can be written as f j j equal to the jth component, okay, the jth coordinate of the node P times the capital Jth value of the gradient of the shape function, okay, or more explicitly it is x j p del n p by del x j. Okay. And in matrix notation, the deformation gradient tensor. Okay. So, here J goes from 1 to 3 and capital J goes from 1 to 3. So, therefore, deformation gradient tensor, as you know, is a 3 by 3, can be written as a 3 by 3 matrix, and that is how you will get. For example, F11 is J equal to 1 and capital J equal to 1, which would mean from equation number 1, F11 is summation over P equal to 1 to n the x1 of node P into del np by del capital X1. Now, this has to be done over all the nodes. Okay. So, in case of brick element, that is cuboid, if your n will be equal to 8, so this will be sum of 8 terms. Okay. Now, we have to compute the material gradient of the shape function matrix NP, okay. Shape functions NP. Okay. So, you have it here. Okay. We have to compute del NP by del capital X, that is the gradient, the material gradient of shape function NP. So, how to do that? Okay. So, using chain rule, you can write del NP by del psi 1 as del NP by del x1 into del x1 by del psi 1, del NP by del x2, del x2 by del psi 1 plus del NP by del x3 by del psi 1. Okay. Similarly, you can write del NP by del psi 2, okay, del NP by del x1 by del psi 2, like this, the other two terms. Del NP by del psi 3, you can write del NP by del x1 into del x1 by del psi 3, like, and then the other two terms. Okay. So, you can write the gradient of the shape function of in terms of the natural coordinates psi 1, psi 2, psi 3 as following three equations. Okay. So, now you can put this in matrix form. Okay. So, the vector, okay, you can put these in this vector. So, this is a vector of the gradient of shape function with respect to the natural coordinates, and you can put this as a matrix into a vector of the gradient of shape function with respect to material coordinate. Okay. And this is a matrix transpose. Okay. Del x1 by del psi 1, del x1 by del psi 2, del x1 by del psi 3 transpose. Okay. So, there are other two rows. Okay. So, in short, I can write this as, okay, this is nothing but del np by del psi. Okay. Psi is a, now psi is a vector, psi 1, psi 2, psi 3. Okay. So, the first array here is nothing but del np by del psi equal to this matrix. I can write that as del x by del psi transpose, okay, and this I can write this as del np by del capital X. So, that is our spatial gradient that we require, okay, and we know NP in terms of psi 1, psi 2, psi 3. So, NP, okay, just after equation 1 we have written NP is function of psi 1, psi 2, psi 3. Once you have chosen a finite element, you will know these function, and this will not change during the course of simulation. Okay. So, this will be always constant during the simulation. Okay. So, you will always have del np by del psi. Okay. Now, I need this. So, what I do? I pre-multiply both sides by del x by del psi inverse transpose, and that is what we are going to do. Pre-multiply both sides by del x by del psi inverse transpose, okay, and this term over here, okay, this is nothing but A into A inverse. Okay. So, this is nothing but second order identity, okay, and then this becomes identity. Therefore, I get my material gradient of the shape function of node P, that is del np by del x as del x by del psi inverse transpose del np by del psi. Okay. Now, as I said, del np by del psi is known to us because np is given in terms of psi 1, psi 2, psi 3, and now I have to compute del x by del psi. How do I calculate that? So, del x, for computing del x by del psi, I just substitute x from equation number 1. Okay. What was that? It is a x is a material coordinate of any point inside the element that can be written in terms of the linear interpolation or the interpolation with respect to the nodal position. So, NP XP summation over all the nodes. Okay. So, I can take psi inside and this becomes XP tensor product del NP by del psi. Okay. So, I already know del NP by del psi, I know the nodal position, and if I carry out these operation, I will be able to find out my del x by del psi. Once I have del x by del psi, I can substitute that here. Okay. I can take the inverse and I can take the transpose, I can get this matrix, and then what I can do, I can multiply by del NP by del psi to get my vector del NP by del x. Okay. That is how we will obtain. Okay. Once you have this, you can find out the expression for the deformation gradient tensor. Okay. So, this del x by del psi in matrix notation is nothing but given here. Okay. So, where xi can be interpolated in terms of the xi value of all the nodes P. Okay. So, in initial notation, equation number 17 can be written as this. Okay. So, once the deformation gradient tensor has been discretized, we can now discretize the other kinematic quantities like the right and left Cauchy-Green deformation tensor. Okay. We can have B and C discretized. Okay. So, how do we discretize C, which is the right Cauchy-Green tensor? C is F transpose F, and I know F is XP tensor product del 0 NP. Okay. And then the other, so this is my F and this is the transpose and this is the other F. Okay. So, I put that as XQ tensor product del 0 NQ. Okay. And summation over P and Q. Okay. So, if I simplify further, I can write this as okay. Okay. So, this I can write as XP dot XQ del N 0 P tensor product del 0 N Q. Okay. Now, XP dot XQ, these are the nodal position of node P and node Q belonging to element E. Okay. So, and we already have calculated the material gradient of shape functions NP and NQ. Okay. So, this can be calculated very easily, and then in initial notation equation 20 is nothing but given like this. Okay. So, in actual setting you will calculate F, and then using that F you can use this formula to directly compute Cij, all the components of right Cauchy-Green deformation tensor. For the left Cauchy-Green tensor, B is FF transpose. Okay. So, F is nothing but XP tensor product del 0 NP, and this F is XQ tensor product del 0 NQ, and then you have to put a transpose, and then when you simplify you get del 0 NP dot del 0 NQ and XP tensor product XQ. Okay. So, in initial notation this is how you get. Okay. So, in actual computational setting you will find out the deformation gradient tensor, and using that deformation gradient tensor you can actually find out all the values of components of B, that is the left Cauchy-Green deformation tensor. Okay. This is just for computational, this is just for understanding, but actual computational setting you will do this. Okay. Now, next the small strain, that is epsilon, and the rate of deformation gradient tensor. Okay. Rate of deformation tensor D can be obtained as follows. The small strain tensor, you know that epsilon is 1 by 2 del u plus del u transpose. Now, del u we have already seen is nothing but u p tensor product spatial gradient of n p plus del u transpose is nothing but spatial gradient of n p tensor product u p. Okay. And the rate of deformation tensor d is the symmetric part of the velocity gradient tensor, and this is given by 1 by 2 summation over all the nodes V p tensor product spatial gradient of shape function n p plus spatial gradient of shape function n p tensor product velocity of node p. Okay. So, the virtual rate of deformation tensor del d is nothing but the virtual velocity of node p tensor product spatial gradient of node p shape function of node p plus the spatial gradient of shape function of node p tensor product the virtual velocity associated with node p summation over all the nodes. Okay. Now, the spatial gradient, okay, so we have a lot of spatial gradient of the shape function, and the spatial gradient of the shape function can be derived like this. Okay. So, remember the material gradient of the shape function was of the similar form is just the same where the material coordinates x have been replaced by spatial coordinate small x. Okay. So, del n p by del x is del x by del psi inverse transpose into del n p by del psi. Okay. And del x by del psi is nothing but x p tensor product del n p by del psi, and this is the initial notation. Okay. So, how we have derived this is shown here, and this follows the similar steps as done for the material derivative of the shape functions. Okay. So, here we have del n p by del psi 1, del n p by del psi 2, del n p by del psi 3 is del n p by del x 1, del x 1 by del psi 1, del n p by del x 2, del x 2 by del psi 1, del n p by del x 3, del x 3 by del psi 1. Like this we can do for the other two equations, and we can write this in matrix notation, matrix vector notation. Okay. And this one over here is nothing but del n p by del psi, this is nothing but del n p by del x. Okay. You can see that we are following the similar procedure as we did previously for the material gradient of the shape function. Okay. So, in matrix notation this can be written as this equation, and now pre-multiplying both sides by del x by del psi inverse transpose, and then recognizing that this one, okay, is equal to identity, I eventually get the spatial gradient of the shape function as del x by del psi inverse transpose del n p by del psi. Okay. That is the derivation for you. Okay. Now, we come to the discretization of the equilibrium equation. Okay. So, right now we have the equilibrium equation in the continuum setting. We like to get the equilibrium equation in the discretized setting, that is in the finite element setting. Okay. So, like divergence of sigma plus b equal to 0, that is the equilibrium equation in the continuum setting. Now, what is the counterpart in the finite element setting is what we are going to look next. Okay. So, recall that the total spatial virtual work expression is given by this equation. So, this is the total spatial virtual work, which is a function of deformation mapping in the virtual velocities, and the first term corresponds to the internal virtual work, the second two terms correspond to the virtual work because of the external tractions and the body forces. Okay. So, this is the external virtual work, okay, external traction virtual work and external body virtual work. Okay. So, these are two. Okay. So, these are these two expressions. Okay. And this is our internal virtual work expression. Okay. Now, equation number 26 can be expressed as the total virtual work. Okay. So, the total virtual work can be split into the internal virtual work minus the external virtual work, and the internal virtual work is the virtual work of the internal stresses, and the external virtual work is the sum of the external virtual work because of the body forces and because of the surface tractions, and equations 30 and 31 give you those expression. Okay. Now, what we do is we use the discretized kinematic quantities that we had discussed in the previous slides, and we can substitute those in equation number 26, and we can get the corresponding finite element discretized our equilibrium equation. Okay. So, we then consider the virtual work contribution caused by a single virtual nodal velocities del p of a typical node p of an element E. Okay. So, what we do? We take a node p of element E at time t, okay, and we consider what is the contribution to the virtual work because of this node. Okay. So, the virtual velocity associated with that node is del p, okay, and then we take equation 26 and we first consider only the internal virtual work expression for an element E, okay, and inside that element we use equation number 7 and equation number 24. So, equation 7 corresponds to the interpolation of the virtual velocities in terms of the nodal velocities, virtual velocities, and equation 24 corresponds to the virtual rate of deformation tensor, and that is also in terms of the nodal virtual velocities and the spatial gradient of the shape function. Okay. So, what we do? We write equation number 28, which is the virtual work coming from element E. Remember, see this, the integration is also, volume integral is performed over the volume of the element. Okay. So, the total virtual work will be nothing but the sum, okay, of the virtual work, let us say N E, or the virtual work of all the elements. And now, we choose one element, and in that element we choose one node P, and we try to see what is the contribution to the total virtual work because of this node P. Okay. So, now I substitute, okay. So, this del E again is P equal to 1, okay. So, this del W E is P equal to 1 to N del W E of P, and this is nothing but del W E of psi comma del V P, okay. This del V P, and this del V P is nothing but N P into the nodal virtual velocity. Okay. So, once we do that, if we substitute equation 7 and 24, the internal virtual work contribution of node P belonging to element E is nothing but integration over the element volume, Cauchy stress double contracted with the virtual rate of deformation tensor, and that integrated over the current volume of element E. Now, we know that the Cauchy stress is symmetric, and then also we recognize that this term inside the bracket is a second order tensor, which is nothing but the symmetric part of another second order tensor del V P tensor product del N P. Okay. Now, we know that this is our tensor, let us say this is tensor A and this is B plus C, where B is the symmetric part. Okay. So, this is B, okay, and there is an anti-symmetric part. So, B is A minus C, okay. Remember, this is our B. So, sigma double contracted with B is sigma double contracted with A minus sigma double contracted with C. So, this term sigma double contracted with C, C is an anti-symmetric tensor, will equal to 0, because sigma is a symmetric tensor. So, sigma contracted with B is same as sigma contracted with A. So, this is our A. So, I can write equation 32 now as sigma double contracted with del V P tensor product del N P. Okay. Now, I can use the following identity. Okay. Let S be a second order tensor and u and v are two vectors. So, S double contracted with u tensor product v is nothing but u dot S v. Okay. In initial notation I can write S I j u I v j, which is nothing but u I S I j v j, and direct notation this is u dot S v. Okay. So, if I see equation 33 and 34, I can recognize S is same as sigma, my u is same as del V p, and my v is spatial gradient of shape function. Okay. So, this is here. So, then using equation 34, equation 33 can be written as del V p dot sigma del n p dv. Now, the virtual velocities are independent of the configuration. This we said at the start of the previous module. So, I can take virtual velocities outside the integral sign and I can write the internal virtual work contribution coming from node P of an element E as del V p dot sigma del n p integrated over the current volume of element E. Okay. In short, I can replace this integral by this vector. Okay. Remember, sigma is a 3 cross 3 matrix and this is a 3 cross 1 vector. So, eventually what I am going to get is a 3 cross 1 vector and this is that vector. I denote this as f subscript int comma p superscript e. Okay. So, what this means is this is the internal force vector corresponding to node P of element E. Okay. So, equation 36 in short can be written as equation number 37. Okay. So, the elemental internal force vector associated with node P of an element E is given by following expression. Okay. Now, remember the internal force vector can be computed using equation 38 and here sigma in general will have 9 components and not necessarily all of them will be 0. Okay. They may be, all of them may be non-zero. Similarly, del n p all the terms are non-zero. So, eventually what will happen, this multiplication over here is between all the non-zero quantities. Okay. We will come to later, we will again revisit this equation later and we will see how this equation number 38 is much more efficient in the computational setting. Okay. Now, next we consider the discretization of the external virtual work expressions. Okay. So, the external virtual work is the virtual work of the tractions and the virtual work of the body forces. So, similarly, we can write the elemental external force or the traction as the integral over the elemental volume T dot del V. And remember, T is the surface traction, okay, externally applied surface traction. Okay. And now, some of the finite element may be in the bulk or the inside the body, therefore, they may not have any surface traction acting over them. In that case, you will have no such contribution. So, this integral only takes place over those elements which are on the surface of the body. Okay. And now, the elemental traction virtual work expression corresponding to node P of element E is given by following expression. So, this del V is replaced by N P del V P and therefore, del V replaced by N P del V V, and then I can write T dot del V P as del V P dot T, and then because virtual velocities are independent of the configuration, I can take them outside and then I am left with this particular integral. Okay. and this I will write as this expression. Okay. This is the external force vector because of the external tractions of node P belonging to element E. Okay. So, this is the elemental external traction vector associated with node P, okay, NP T D A. Okay. Now, the second part of the external virtual work is because of the body forces, and we know the elemental external body force body virtual work expression is given by following integral. Okay. And then for a node P of element E, del V is NP del Vp. Okay. So, this expression becomes this, and then we can take del Vp outside, and this this integral I can denote by the following vector, which is the elemental external body force vector associated with node P. Okay. So, corresponding to the external virtual work, we are getting two force vectors, one is because of traction and one which is because of the body forces. Okay. Remember, these integrals are carried out over the elemental area and volume of the element E. Okay. Now, I can substitute equation 37, 39 and 41 in equation number 27. Okay. Once I do this, the virtual work of node P belonging to element E is del Vp dot internal force vector of node P belonging to element E minus del Vp dot the external force vector because of traction of node P belonging to element E minus del Vp dot the external force vector because of the body forces at node P belonging to element E. Okay. So, I can take del Vp outside the bracket and I am left with following quantity inside the bracket. Okay. So, these two I can combine together and I can write them as the one force vector, that is the external force vector, which is nothing but the sum of the tractions component and the body components, body force component. Okay. Once I do this, okay, I can get the virtual work contribution from node P belonging to element E as del Vp dot the internal force vector because of node P belonging to element E minus the external force vector of node P belonging to element E. Okay. And then these are the explicit expressions in direct notation and these are the indicial notations. Okay. And we note that the stresses in the internal force vector. Okay. So, the stresses in the internal force vector, that is here, can be found using the constitutive relation. Okay. So, in our case we are using an compressible neo-Hookean material for which we have already derived the Cauchy stress as following relation given by equation 50 or in indicial notation given by equation number 50. So, what will happen? To compute the internal force vector, you have to first get the stresses. Okay. To get the stresses, what you need to first do is you need to get the B and J. B and J both you can obtain if you have got the deformation gradient tensor F. Okay. Then J is determinant of F and B is FF transpose. Okay. So, inside a finite element setting, the first thing you will get is the deformation gradient tensor, then you will obtain J, then you will check for the value of J and you will do check whether you have a valid deformation, and then you will find out B, and using B you will find out sigma. Once you have found out sigma, you can find out the internal stresses. Okay. that is F internal. Okay. And if that element has some body forces, you will find the external body force vector, and if that element belongs to the surface of the body, then you will find the external force vector because of the external tractions. Okay. Then the assembly of the spatial total work over all the elements which are connected to node P. Okay. In a finite element setting, okay, if you have a node P, then a lot of elements E1, E2, E3, E4 like this, a lot of elements will connect to node P. It may also happen that your node may belong to a corner element. In that case, P will have only one element, okay, or in general P may have different elements connecting to it, and then if we take the contribution to the spatial virtual work because of all the elements which are connected to node P, then we know add the virtual work contribution over all the elements from E equal to NPE, where NPE is the number of elements connected to node P. Okay. So, the number of elements connected to node P. Okay. So, this information has to be there, and then I can substitute the expression here as del V P dot F internal minus F external. Okay. Now, virtual velocities I can take outside, okay, and this is the integral over all the elements connected to node P of the internal minus the external force vector. Okay. So, this finally I can write this as del V P dot F internal, total internal force at node P minus the total external force at node P. Okay. Next I can do the, okay. So, next I can assemble the spatial total virtual work over all the nodes, okay, to give us the total spatial virtual work. Remember, this is the total spatial virtual work, and this can be obtained as the total virtual work of all the nodes. Okay. So, this is the contribution to the total virtual work for node P, and this when integrated over all the nodes. Okay. Here NP is the total number of nodes in the mesh. Okay. You may have thousands of nodes. So, this NP may be 1000. Okay. And when you substitute this expression from the previous slide, I can write in short this as RP, where RP is the residual at node P. Okay. And assembly over all the nodes give me the global internal force vector minus the global external force vector, and the difference of the internal and the external force vector is nothing but the residual R. Okay. Where the internal force vector, as you can see here, is the assembly over all the nodes. The external force vector is the assembly over all external forces of all the nodes. Okay. And then the residual is nothing but the difference of the internal and the external forces. And now, my objective is to reduce this residual, to bring this residual equal to 0. So, that when residual goes to 0, the internal forces will balance out the external forces, and that is when you achieve your equilibrium. Okay. So, this is the explicit expression of the global internal force, global external force, residual and virtual velocity vector in the previous slides, where each of these here correspond to one particular node. So, this correspond to node 1, and this correspond to the final node in the mesh that you have. Okay. Since the virtual velocities are arbitrary, so equation 56 gives us the complete nonlinear discretized equilibrium equation as Rx equal to F internal minus F external. Okay. So, the internal and external forces are the nonlinear functions of x, and then equation number 61 gives you the finite element discretized continuum equilibrium equation that we had, which is divergence of sigma plus b equal to 0, and this is the corresponding finite element discretized part, and x is the vector of unknowns, okay, that we need to find out. Okay. So, this is the unknown at node 1 and this is the unknown at final node n p. Okay. So, we can derive an alternate expression for equation number 38 in matrix form. I can write using Voigt notation the Cauchy stress tensor in the vector form like this. So, instead of writing 9 components, I can express them as 6 components, because the other 3 are symmetric, because sigma 1 2 is same as sigma 2 1, 1 3 is sigma 3 1 and sigma 3 2 is same as sigma 2 3, and this is the rate of deformation tensor and this is the virtual rate of deformation tensor. Okay. So, this virtual rate of deformation tensor, which is given by the following expression, okay, and this is the indicial notation. I can write them explicitly as del d 1 1 as del v 1 p del n p by del x 1. Okay. This you can do from the indicial notation. So, del d d 2 del d 2 2 is given by this expression, del d 3 3 is given by this expression. This is 2 del d 1 2, this is 2 del d 1 3 and this is 2 del d 2 3. If I write all these 6 equations in matrix form, I can express my rate of deformation tensor in vector form as following expression. So, this is what I defined, this is the matrix, okay, and this is the virtual velocities. So, this matrix I can write define a matrix called BP. Okay. So, this is BP, the matrix B associated with node P into virtual velocity del Vp. Okay. Now, the internal virtual work expression, which was given like this same can be written as del D transpose sigma, okay, and del D from my previous slide is Bp del V, okay, del Vp. So, this is Bp del Vp transpose, this is sigma, and now del Vp transpose, this becomes del Vp transpose Bp transpose sigma, and then I can write this as del Vp dot Bp transpose sigma, and virtual velocities I can take outside the bracket, and this is my relation B transpose sigma dV, and this is nothing but this should be same as the internal force vector corresponding to node P of element E. Okay. So, you see here we get an alternative expression for the internal force vector of node P belonging to element E as integral over the current volume Bp transpose sigma dV. Okay. You note that although this equation is what you find mostly in the books, it can be seen from equation 67, okay, which is here that there are a lot of zeros present over here. Okay. There are a lot of zeros you see here. So, that due to the presence of a number of zeros in the matrix B, equation 70 is computationally more expensive than equation number 38. Okay. So, equation 38 in the actual computational setting is what we use. Okay. 70 is what is mostly present in the finite element text. Okay. Thank you.